Much. Can you hear me? Okay. So yesterday we discussed several aspects of microaerial vehicles, mostly the dynamics, how we do control, nonlinear control, how we do planning, and then I told you about the challenges in state estimation. One big problem is when you try to build robots that are capable of estimating their own state, they become really heavy, like this one, which has a laser range finder and a RGBD camera system on board. This weighs about 2 kilos. It's a little less than that, consumes about 400 watts, and that poses challenges in terms of mission life. And given the state-of-the-art in lithium polymer batteries, this is not a viable design. So that really led us to discussion on size, weight, and power constraints. And so today, what I'd like to do is to start talking about vision-only based estimation and control, and then move on to cooperative control, swarms, and then some applications. I'm going to turn off the audio. Okay. So again, towards the end yesterday, I told you about this design that we kind of converged on. So this is the lightest weight autonomous vehicle you can find. I'm not sure why this part is being hidden. Oh, maybe it's just my slide. Oh, never mind. It's in the picture. That's the end of the wall. I couldn't see it. So this design is essentially the simplest quad rotor you can build. It has on board roughly a cell phone grade processor, a netbook grade processor with 2 cameras and an IMU. And in theory, this has on board the hardware that should allow the robot to essentially reason about the environment and determine its state relative to the environment. So I want to show you basically what we've been able to do with this robot, and this is mostly the work of Xiaoji Shen, who is now at Hong Kong University of Science and Technology as an assistant professor there. So you can see outdoor, the robot is able to pick up some features. This is under trees. And then inside, it's able to see some features. And yesterday, I talked about the framework for doing simultaneous localization and mapping, which essentially allows you to think about the state estimation problem as a nonlinear optimization problem with an underlying graph structure. And you'll remember that the graph structure relates robot poses, positions, and orientations to features that it sees. And so these are examples of features that you might see from different poses. To give you an idea of what it really looks like in real time, here you'll see the robot moving around, and this is inside our lab, and it's tracking these features. There are green features which are tracked at a higher rate than the blue features because the 2 cameras run at different rates. And here you'll basically see the 2 poses that we get, estimates that we get. So one of them is vision only, the other one is vision plus IMU. But basically this is happening at around 30 hertz as the robot's flying around. And you can see the flight here is quite aggressive. Roll angles and pitch angles of about 40 degrees in these flights and about 2 meters per second flight inside our lab. So this is the basic idea. So with those features, you should be able to extract your position and orientation of the robot, and this has to happen at 100 hertz. Obviously, vision only provides updates at 30 hertz, but your IMU provides updates at 100 hertz. And last time you'll recall, we have this unscented common filter that essentially pulls together these estimates, allowing 100 hertz update of the states, which then feeds our controller and then eventually our planner. So here are some sample experiments. So the one on the top left shows indoor flight at 4 meters per second. So this is a pretty fast speed. This is like running speed for most of us. So down the hallway, autonomous flight, again, triangulating off of features in the environment. This is outdoors. The challenge here is you can see with the foliage being disrupted with the downdraft, a lot of the features are actually moving. But if your cameras are facing forward, there are enough features that are stationary that you can track frame to frame, and this allows localization. And then the bottom left, here you see navigation in indoor environments, but these are more three-dimensional. Again, the wooden paneling here actually gives you repetitive structure, and so that's bad, but all other surfaces actually are good enough to get you features, even in fairly boring indoor environments. And then an example of indoor and outdoor navigation. So here, the reconstruction that you're seeing here, the map that's being generated here is not being generated on board. So on board, you only have sparse features, and you're essentially triangulating based on that. But if you feed all that data off board to another machine, then that machine can actually do this reconstruction. And here the main challenge really for us is computational resources. If you can put a lightweight GPU on board, you can do all of this on board. And I think it's a question of time before companies like NVIDIA come up with processors that we can actually reduce to a cell phone grade size and power constraints. And we should be able to do all this reconstruction, dense reconstruction on board. The one caveat about this is you really cannot use these maps for doing trajectory planning or obstacle avoidance. So in each one of these experiments, the human operator is essentially looking at what the robot sees and saying, go here, and then there. So the high-level planning is done by the human, and then the low-level trajectory planning is done by the robot. And that's because if you just use vision information, it's very hard today, with today's small processors, to do a complete dense reconstruction of the environment, to do motion planning and to do obstacle avoidance. But you can do it at a finer level, the trajectory planning level. And that's sort of where this work is headed. I think it's a question of time before we can do all of this on board. So in general, if you go outdoors, then you might think about using other sensors than just vision. So one of the problems with vision, of course, is it doesn't work in the dark. It doesn't work when it's raining. It doesn't work if there's smoke. But lasers work there, and so our strategy here is essentially to use all the sensors that are available and then fuse this information when possible. So you'll see these trajectories are now colored, and the color segment tells you which sensors are active. So when it's green, for example, it's just the vision and laser that's active because there's no GPS in these buildings. When you get into the open field, then in fact it's red, in which case all the sensors are available. So depending on what is available, you can do the reconstruction, and there will be times that only vision is available, only laser is available, and only GPS is available. Of course, in all cases, the IMU signals are actually pretty good, and that is what bootstraps this estimation process. So this is not vision only, but in segments of the trajectory, it uses only vision, and that's important, even though your robot might be bigger and have a laser on board. Then lastly, in our class, in fact, we've used this to, and again, you can look at this website for materials in the class, but what you see here is our robot essentially navigating using only a camera, but having some structure to the environment. So these are April tags, which are like QR codes that you can print out on standard paper. And you can cover your whole lab or your living room or your kitchen with this. And if you have a robot with a downward-facing camera, and you can walk it around, you can train the robot on the map, it'll know which feature is where. And you can see these squiggles here are to enable better velocity estimation, optical flow. So a combination of squiggles on the ground, scribbling, actually equations work very nicely because they have a lot of curves, like integrals are great, Greek letters are great, a lot of curves. That works very nicely. And then these tags are all unique, and you can print them out in whatever shape you want. And in our lab, in our class, by the time students reach the end, their goal is to essentially get autonomous trajectory planning, control and estimation using this platform without the motion capture cameras. And again, all of this is done on board with a gumsticks processor and off board using a laptop with Wi-Fi communications in between. So that's where sort of vision-based processing and for state estimation is today for small processors. One other thing I might point out is, so this is work by Giuseppe Loiano. This is a robot, an off-the-shelf robot with an off-the-shelf phone, but it's not any phone. This is one of the Google Tango phones. I don't know if you've seen this. It has a RGBD camera built in, but now phones are getting so good that you can actually use them as absolute pose detectors, right? So there's no vision software that Giuseppe wrote for this. He just took this phone, he took the software coming from that, and he wrapped around a control algorithm and a filter. So all the processing that's being done on board is essentially tying in vision as a state estimator, and then the UKF, the unscented common filter, which essentially uses IMU information matched with the vision pose estimation, and I'll tell you how that filter works in a minute, driving off-the-shelf robot. So again, the piece on board is off-the-shelf, the quad rotor is off-the-shelf, not ours, and we simply plug this into that. Literally, it's a USB connection between the Odroid processor on board and the phone. And so robotics has reached a point where consumer electronics now can literally be plugged into a robot and make it autonomous. So I think this is great for us that companies like Samsung now are producing things that actually benefit robotics as opposed to cluttering the internet with pictures and videos. And again, the Google Tango phone allows us to create depth maps like this, which again, so if somebody had told me, 10 years ago, even 20 years ago, that pretty soon you'll be able to buy a phone off the shelf, plug it into a laptop, and then send it into a room and create maps like this autonomously, I would have asked them, what have you been drinking lately, right? But it's just incredible how technology has progressed. So let me just again tell you, this is it's a school, so let me just tell you what our students do in class in 620. Basically, this is what they end up doing. So this is a simple exercise, and for some reason this video is not playing. But essentially, they're told a series of tasks to perform on a carpet like this. Okay, this video is not playing, but you get the gist of it. So this is the carpet with tags, and the key idea is to use a common filter and a variation of that to accomplish this task. So just to do a refresher on what a common filter entails, essentially it allows you, based on your estimate of the state at a particular time and based on measurements and inputs that you're commanding, to infer the state at a subsequent instance. So if you know the state at t-1 on the top left, can you find the state at time t on the bottom left? So this involves two steps. So one is a prediction phase. So it's assuming you know what the input is, so you know how many steps you're taking, that is u sub t. So in our case, it's what current we're sending to the motors, what speeds we're spinning the propellers at, and you have a model, and in the common filter, it's a linear model. So obviously, we've seen the nonlinear model yesterday, but what we're saying here is that we're going to approximate it by a linear model in this very small time interval between t-1 and t. And n sub t in the prediction phase is essentially a noise term, and the big assumption here in the common filter is that the noise is additive and it's Gaussian, right? In other words, the process is essentially a white noise and described by the statistics of n sub t. The second assumption, of course, is that the prediction model is linear. So based on this prediction model, you can infer the state at x sub t without making any measurements. So if I take 5 steps, that means I must have walked roughly the equivalent of 5 steps. And that is captured in the statistics over here. So this is essentially the expected value of where I might expect to be after 5 steps. And this is the covariance associated with it, assuming that I applied the input u sub t at time xt minus 1. So if I have the statistics at time t minus 1, I can find the statistics at t. This is the covariance at t minus 1 and then t. But now I have an observation, and in our case it comes from a camera. So if you make an observation z sub t, then essentially you take the measurement z sub t and you ask what would the measurement have been if I had been at x sub t bar given by this value. So this discrepancy is essentially the difference between where I think I should have been after 5 steps, right, and where my sensor is telling me that I am. So that discrepancy is this term, and you multiply it by a gain. So this is the innovation. This gain is called a common gain, and you essentially correct what you predicted by adding this term, and that gives you a new prediction, a new update at time t. So you do that for the expected value. You also do that for the covariance in a similar way. Those of you who know what common filters is all about don't need this. Those of you who don't know what common filters is probably should take this as a motivation to try and read up more about this. But this is sort of central to all the estimation work we do. So there are 2 assumptions here. One is the linear model in all of this, right? The observation model is linear. The prediction model is linear. The second assumption is that your noise is additive and Gaussian. It's a white noise process. Both those assumptions are wrong. In the extended common filter, we try to rectify one of those assumptions. And that assumption that we're rectifying is the assumption that the dynamics and the observation model are linear. So instead of taking the linear model, what we do is we take the nonlinear model for the measurements, the nonlinear model for the process, and then we linearize it. All right? So the prediction phase essentially asks, where would xt minus 1 end up after propagating it through this nonlinear noise model, process model, to get to x sub t bar? And then it also asks, what would the update be? And essentially, both these steps involve linearizing of this function of f, this function f, and the function h. So that's the extended common filter, and that's what the students end up using in class. A variation of this is the unscented common filter, which I've talked about before, and think about it as a way of using common filters for nonlinear models, except here you have to linearize. In unscented common filters, what you're essentially doing is sampling the noise and the statistics at a finite number of points. Instead of just linearizing at one point, you're taking multiple points. And the good thing about that is it's actually a little more robust, and you don't have to do the linearization, which in our setting can be truly complex, involve lots and lots of calculations. And so the unscented common filter, if you know how to use it, ends up being much better. But this is actually simpler to understand, and that's why we have students do this in class. So that's the EKF. And I'll just try to explain how the vision-based estimation framework fits into the EKF. Okay? So here is the state vector. So this state vector consists of the position of the robot. X2 is the orientation. Now, we're not doing crazy things like I was telling you yesterday, like going upside down. So Q, we can just let be the 3 Euler angles. Okay? X3 is the derivative of the position, so that's the velocity. So you've got position, orientation, and velocity as part of the state. Okay? Before I come to the next 2 variables, let me remind you that the rotation matrix is a nonlinear function of the 3 Euler angles. And that's what that is, right? So the Q is the 3 Euler angles, theta, phi, and psi, and this is the rotation matrix. So that's the kinematics. So if you look at the angular velocity in the body frame, so that's omega. This is the body frame angular velocity, the roll, pitch, and yaw velocities in the body frame. Those are related to phi dot, theta dot, and psi dot by this matrix. And by differentiating this and doing some manipulation, you can come up with that. Okay? Now the question is, what do you measure? So if you have an IMU on board, it includes a gyro that gives you some estimate of the angular velocity. So you're actually able to measure this, right? So the gyro measurements are written as follows. Here's the measurement obtained from the gyro. This is the actual angular velocity, which is over here. However, you can have a bias term, B sub g. This is the bias of the gyro. And remember, the great thing I showed you in the pyramid diagram, the great thing is that things are becoming less expensive. But the bad thing is, the cheaper the gyro, the worse the quality, right? You can pay lots and lots of money for a heavy gyro that doesn't drift. Our gyros are not, remember, weight is a big issue for us. So there can be a bias, and there can be an additive noise, and this is modeled as a Gaussian for us. So this is our sensor model, and B sub g, we don't know what B sub g is, so we let it be part of the state, and we try to estimate that. Then the last piece of the puzzle is the acceleration. The IMU measures accelerations, but again, it's not a perfect measurement. A sub m is the measured acceleration in the body frame. So if I find the actual acceleration in the inertial frame, I transpose it into the body frame, but then I have to add a bias of the accelerometer and then a noise term. And again, this bias becomes part of the state. So the gyro bias and the IMU and the accelerometer bias keep getting estimated at every time instant. We allow those to drift. And we also model the noise as an additive term there. So that's essentially the entire model. And again, I want you to remember that the derivative of Q and P dot are essentially like inputs. And although we may not measure the real inputs, which are the propeller speeds, what we're essentially saying is we can measure the angular velocities and the linear accelerations, which are derivatives of those two guys. And then the vision measurements allow us to measure where we are depending on what tags we see, what our orientation is, and what the linear velocity is. So the linear velocity comes from optical flow. So if I look at the texture, all the squiggles on the carpet, I can measure velocity. I can measure position by looking at 3 tags and triangulating where I am, and I can also get orientation that way. So this is the entire model. It's nonlinear because primarily of this mess and this mess, right? But we're assuming that the noise is Gaussian. You can see that this is Gaussian. And the vision building block we're abstracting out, and we're saying we can get these measurements directly plus an additive noise. I forgot to put that in. But again, we're assuming the noise is always Gaussian. So this lends itself to the EKF framework, and this is what allows our students to actually complete this exercise in 1 semester. Okay? Questions? I went through this pretty quickly, but it takes maybe 1.5 months for us to do it in class. Yes?
Why the carpet has this, beside the marks, it has some things?
So this part,
yeah, they have some drawing of it.
These things allow us to measure texture, velocities.
Okay.
So actually all our videos, I want to show you, I often joke with my students that our robots understand equations, because if you look at this picture, you see this video here? Oops. So you look at the density of features, a lot of features on the board, right? Because all our equations are there. It's like our robots are reading the equations. But the reality is anytime you have text, you get flow, you get features. The corners are very, very conspicuous against the white background. And they form good features. And likewise, the same thing here. Actually, one of my students actually prints equations on this carpet. But this one is, this is something that they download and they print and then they stick them together. Yeah. Any other questions?
On the slide 10, does it flag autonomous?
Slide 10. Oh, a great question. So again, the onboard reconstruction is not done here. So yes, it's not perfectly autonomous. The human is essentially saying, I want you to go click, 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 and then the robot finds points through that trajectory. So again, with sparse visual information, there is no way, for example, for you to detect like a window in front. Or if you have a white wall in front, neither the camera will not see it. But in that case, the laser might see it. So, but most cases we don't, right now we're not doing the reconstruction. Potentially this can do because you have the laser, you can do full reconstruction, and it can be completely autonomous. So technically this is partially autonomous. Just in case you're interested, I can share with you real data from our IMU to show you. So this is actually a pretty expensive IMU. And I'm sorry, the picture is pretty bad. Actually, I have to go to my screen to read the numbers here. But you can see that actually, I don't know what you can see. So if you look at the bottom left, that's the z-axis acceleration. So that should be 9.81. And it's essentially varying between 9.64 to 9.97. That's sort of the variation. So there's a lot of variation there. So the one on the left is the gyro. The one on the right, the one on the left is the IMU. The one on the right is the gyro. And you can see the x-axis acceleration in the top left has a noticeable drift, right? And that's the B sub g term. The x component of B sub g, which we're again estimating. And if you don't do that, if you don't track those biases, you'll end up with estimates that are consistently drifting. So it's important to correct for these. Okay. Yes?
How do you know how to switch between GPS plus vision, GPS plus laser?
Each sensor is characterized so that we can determine what the errors are associated with that sensor. So that's pretty key. So in cameras, you take features and then you reproject them into 3D space and then you look at the errors. That gives you an estimate of the covariance. Likewise, for the laser, you can use sort of this Fisher information to get you. So every sensor comes equipped with an estimate and a covariance, assuming the world of Gaussian noise distributions. So then, if you have a bunch of sensors giving you similar estimates and you're trying to figure out how to combine them in a linear Gaussian setting, that's a fairly established approach to doing that.
So it looks like you're switching. Sometimes you forget GPS.
Right. So, and technically we're not switching. If the covariance of one of the sensors becomes very, very large, we basically ignore it. Yeah. So technically we could fuse that, but I'm just showing you that to show you areas where one or more sensors fail. Okay, so let me start talking about cooperative control by telling you, so in multi-robot systems, there are 3 C words that are interesting. One C word is coordination, the second C word is cooperation, and the third C word is collaboration. And here are definitions from the Oxford Dictionary. I know many of you are not native English speakers, but I guarantee you, even if you were native English speakers, the differences from these 3 words are somewhat blurred, right? So there are people who do cooperative control, some people do collaborative, and the same thing for estimation, right? So I have my own spin on this, and it's going to lead somewhere. I'm not going to give you a lecture on the English language. But I want you to look at these 3 words and look at the definitions. In one case, it has to be about the ability of using different parts of the body. So let's assume that means robot. Together smoothly and efficiently. So a bunch of different robots, we want to use them together smoothly and efficiently. The second piece, and this is really semantics, the process of working together to the same end, the action of working with someone. So what's the difference between working together and working with someone? There really is not that much of a difference, but colloquially, when you write a paper with somebody, you don't cooperate, you collaborate, right? But when you cooperate with somebody to pick up a piece of furniture, like a sofa, you don't collaborate, you cooperate, right? So it depends on what task you're performing and what your goal is, right? So this is, again, based on usage. So I have my own definitions. So let me start with coordination. This is the most fundamental way in which robots can essentially work together. Imagine a task with a cost function, and everybody knows what that cost function is. Okay? Imagine that your robots are interchangeable. Imagine that the task is the same, so I'm going to take M tasks and N robots, and we want the efficacy, the performance of the task to improve as you increase the number of robots. And you want it to increase roughly by n. So I want to show you a simulation, and I want to see if Luis recognizes this, because this is his work. So these are identical robots, 100 identical robots, and they've been tasked to approximate a shape. So the common cost function is how well they can approximate the shape. They all have the same cost function, and what do they have to do? They have to coordinate. It doesn't make sense for two robots to be really close to each other when they can be far apart and do a better job of approximating the shape. And they have to avoid each other. They have to avoid collisions. And you can see these 100 robots collaborating, coordinating, cooperating, call it whatever you want, but I'm going to call it coordination. And they're able to form the shape. Now, in this case, the technical idea that's being used is the ability to synthesize controllers based on potential fields. So there's 100 robots interacting with each other. They're being affected by how close they are to their neighbors and how close they are to the target shape. And a combination of those allows them to trace this fairly complex shape. So this is coordination. All the robots are doing the same thing, and they're just trying to make sure that they do it efficiently and not get in each other's way. Another example of coordination, and this is Luciano's work, where now we have 100 robots, and the task is to essentially cover this area. So the exact algorithm that's being used here is the emulation of a fluid flowing through a fairly complex environment. And these robots are particles in that fluid. They've been carrying around with the fluid. You don't see the fluid, you just see the robot particles. And you can see when they get to the actual shape, they're able to distribute themselves into that shape of interest. And again, what they're trying to do is cover this area. Once again, there's one task. The robots are coordinating with each other, and they're essentially solving the Navier-Stokes equations that determine the mechanics and imagining how they would move if they had to obey the Navier-Stokes equations. That's essentially what is going on. That's the underlying coordination mechanism. In a minute, you'll see real robots trying to do the same thing. Now, we don't have 150 robots in the lab, much smaller subset, but they have a holding area here, and they're moving around like somewhat in a strange way. That's because they're interacting with each other. But I want you to believe that they're part of this fluid that's flowing out of this source into a sink which is back there. And essentially they're coordinating. They're trying not to get in each other's way, where the task is essentially coverage. Again, common cost function, single task, identical robots, and essentially they're coordinating to perform this complex task. Right? So that's coordination. At least that's my definition of coordination. Let's go to cooperation, where I'm going to assume now that there are multiple tasks that need to be performed, and your mission is as successful as the sum of the individual task missions. So the mission reward is the sum of individual task rewards. But now individuals have to compromise, because imagine we all have to go out and get some food, right? I might have to decrease the amount of food that I get myself to make sure that the collective food that we have gathered is bigger. So essentially I have to give up my individual rewards to maximize the team's rewards. So here's an example where that happens with ants, not with robots, but you can see these ants spontaneously forming a team, gathering. This is actually a fig. What's a fig? Does everybody know what a fig is? Huh? Figu. There you go. So they essentially recruit their neighbors. They carry this back to their nest. And they do this for prey as well. Sometimes you can see them carrying large insects. Individual ants are not strong enough to do that, but they know if they stop taking their little bits of leaves or whatever else that they're doing and instead collaborate or cooperate to carry this big thing, the young at the nest would actually benefit a lot, and that's what they're doing here. And this is a spontaneous mechanism that emerges in ants, and we'd love our robots to be able to do this. So we've also done this in the lab, and this gentleman is one of the co-organizers, Professor Pereira. This was many years ago. I wish students were as productive as you were back then, but this was quite remarkable. So what is happening here is the task is, and these robots are fairly dumb. They don't have any grippers or anything like that, but like the ants, they want to take this funny-looking object, not a fig, but this triangular box, and take it from one position to another. And what they're essentially doing, let me replay this video, they're essentially trying to interpret their relative positions and trying to figure out how their relative positions is constraining this box by looking at their neighbors. The reason they have these funny hats is because there's a camera that's telling the robots where those funny hats are, and they can determine where the neighbors are, and they're determining what configurations are compatible with the object being trapped inside. And then they're moving the trap. A similar strategy to what ants might be using for carrying objects, except ants actually have mandibles for grasping, and these robots don't. And in the lab, we've done this with quad rotors as well. So this is cooperative transport instead of, again, picking up little bits of pieces, 4 robots coming together to pick up this fairly complex object that individuals could not pick up on their own. And here you see them grasping, and they have fish hook grippers, so fishing hooks. They dig into the object, they pick it up, and again they have to cooperate to carry this. And they're essentially sacrificing their own objective functions to make sure that the team objective function is maximized in some way. And then lastly, I want to talk about collaboration, where individuals actually may not even have the same goals and tasks. In fact, individuals may not be able to complete a task. So oftentimes in research, you might have a theoretician collaborating with an experimentalist, because the theoretician doesn't know how to do experiments. The experimentalist wants the theoretician to explain some of the data, right? So they too have their own functions, but unless they collaborate, they're not going to be able to do whatever it is that they're trying to do. The same thing here. There's heterogeneity. There's a theoretical robot and experimental robot, if you will, and they're collaborating to do something. And now your task increases superlinearly. Before, individually, they couldn't do anything, but if you put them together, suddenly you get something which you could not have done alone. So we have several examples of this. The first example of this was actually work done by Tom Sugar, where these robots look like they came from the last century, and that's because they did come from the last century, right? This is like, this was running the preemptive version of DOS, 6.1. I don't know if anybody remembers what DOS is. If you do, then you don't want to acknowledge it, right? So let me see if this video plays. It's an ancient encoder, but yeah. So these are old robots. Some of them are only capable of carrying So this one has a forklift. This one's only capable of pushing. And that's Tom Sugar, who's now a professor at Arizona State. And they're basically coordinating to carry this Dell computer box. Yes, computers used to be that big back then. Something even more complicated that Luis did following that. So this is, again, a paradigm for coordinating, dynamically exchanging roles depending on the task. And although the word here says coordination, in reality this is collaboration, because every one of these robots does something very different. They're not identical. So, Luis, if we rewrite this paper, we should call it collaboration. Okay? So these are some ways that you might imagine robots coordinating, cooperating, or collaborating. And I'll tell you about one other piece of recent work, which is a collaboration between my group and Professor Mark Yim's group. So these are robots that are sized of shoe boxes, right? But if you scale up a shoe box, you get something that looks like a shipping container, which you see on the backs of trucks. So the idea that the Navy has is that if we have shipping container-sized robots, they could form docks in the middle of the sea, in the middle of the ocean, to help in humanitarian search and rescue or oil cleanup and so on. Here, these robots are collaborating to form a bridge between one end of the swimming pool and another end of the swimming pool. And you'll see that once they form this bridge, they'll allow a second type of robot to drive across, right, which you could not have done otherwise. So this is a little bit of a gimmick, but in reality, the paper actually discusses how to get these robots to form a given shape so that they may satisfy a certain task. And so we've thought about how you might form airstrips for landing, for aircrafts to land in the middle, how you might form bridges, or how you might form depots to service for various humanitarian missions. So before I go any further, let me pause and see if there are any questions about these definitions. Okay, no. So let's move on. So let me go back to flying robots and tell you about some coordination work that was done by Quentin Lindsay, who is now at Aero Environment. So this particular experiment shows 3 robots essentially coordinating to construct a 3D structure that's been specified by the designer. Now, this structure essentially consists of truss-like elements with magnetic fasteners. So you're allowed to take cubes and compose them in different ways. Once you provide the robots with a drawing, the robots decide which robot picks up what part and assembles it where to construct the structure. So here you will see that there's a place where these elements are stored, those elements are stored, these are columns, these are beams, and the robots, and this is sped up here, 3 different structures, and in each case, all you have to do is specify to the robots what structure to build, and then the robots decide how they pick up parts, and this question of who does what and when is determined automatically, and the question of coordination, how do I navigate without bumping into my neighbor, is also determined automatically. Now, here, it's done inside the lab with a motion capture camera system, so perception is a solved problem here. But the problems of planning, control, and coordination are being done autonomously. So it's worth looking at this in greater detail, and I want to start by telling you what has to happen behind the scene in order for this to happen, right? So let's say I have 3 robots starting off from position S1, position S2, and position S3, and let's say these are the 3 goals that they need to go to. So the first thing, and this is where the parts are, let's say this is where the columns are, this is where the trusses are, and so on and so forth. The first thing that has to be determined is who goes where, right? So that means these goal locations have to have numbers associated with them, G1, G2, and G3. And the second thing that needs to happen is, after you do this assignment, so this assignment matrix essentially is a 1 if robot I is assigned to goal J, or 0 otherwise. The second thing that needs to happen is these trajectories that have to be designed simultaneously. And you can't do this independently because you have to make sure that these trajectories are such that there are no collisions. So each robot, let's say, has a finite extent. You have to make sure that they don't bounce into each other, right? So the safety condition here is that no robot can appear within 2R of another robot. We're assuming that the radius is the same. These robots are homogeneous. This is a 2D picture, but I could do the same thing in 3D. And then lastly, we want some notion of optimality. Yesterday I told you about these minimum snap trajectory measures. So what we're looking for are trajectories that are smooth and satisfy some snap-like or minimize some snap-like measure. Okay? So that's the problem that needs to be solved by Quentin when he was thinking about how to do this, the building up of these structures. So the key challenge here is the assignment problem and the planning problem have to be done concurrently. I presented it sequentially. I said, well, let's first assign these labels, and then let's do the planning, but actually they could be done together. So let's try to find out what is involved in doing this together. So I've got my 3 robots, 3 goals, right? And I have a bunch of obstacles too. So how do I plan these trajectories? So for a single robot yesterday, I told you how we can formulate the cost function as an integral cost function, how I can go through hoops, how I can write this as a quadratic program, and you believed me, right? But let's see if that actually works for this kind of a setting. First question is, how do you model obstacles? So our approach is we take all quadrotors and we box them up into polyhedra, into convex polyhedra. In order for convex quadratic programming to work, you want convexity, and this is the obvious way to do it. We do the same thing with obstacles too. So everything in the world is decomposed into convex polyhedra. So if you take a convex polyhedron, each convex polyhedron has multiple faces. And for every face, you can write an equation of this type. This is essentially a linear equation, which is inequality that's telling you that the robot at time t sub k must be on one side of this face, right? So this is the equation of a plane. Ax plus by plus cz is equal to d, but I take the equality, make it an inequality, and I'm essentially saying this robot at time t sub k should be on this side of the face f. So this f denotes the face f, the n denotes the face m, and o denotes the oth obstacle. I have to do this for every single obstacle. But if you want to avoid a particular polyhedron, you don't have to avoid every single facet. Right? If I take this obstacle, which has many facets, many faces, all I need to do is be on one side of the obstacle with respect to one face. So in other words, I can be on this side of this face, or that side of that face, or this side of this face. I don't have to be on the outward side of every single face in the obstacle. Right? So that lends itself to rewriting this equation as a mixed integer inequality, so where m is a very, very large constant, let's say 1,000,000, and this is a binary variable. So if this binary variable were 0, that would be like saying this term is not there, and the robot is avoiding this face of the obstacle O. But if that binary variable were 1, this equation is trivially satisfied, which means the robot is ignoring this particular face. But we want to make sure that the robot avoids the obstacle. So we're going to insist that the sum of the binary variables is equal to at least 1 for a particular obstacle. So that gives rise to this. So we essentially make sure that at least one of these for every obstacle is equal to 0. Right? And the others, I don't care. It can be 1 or 0, I don't care. So that's a mixed integer inequality. And now I rewrite my quadratic program, except in addition to this and this, I have a whole bunch of these binary constraints, right, which is obtained by these binary variables. So what's the problem with this? If you have n robots and m obstacles, one problem is that the dimensionality of the space increases linearly with n, which is to be expected, right? And there's no free lunch. Size of your quadratic program will keep increasing. But if you have good solvers, this is not where the problem is. The problem comes in really with the number of obstacles and the number of neighbors. So the number of potential interactions is n squared, and the number of binary variables you have to write for obstacle avoidance is n times m. So if an obstacle has f faces, then for every obstacle you'll have f binary variables, and then you'll have m times f binary variables for your m obstacles. And if you have n robots, for every robot you'll have to have m times f binary variables. So the number of binary variables in an environment like this quickly grows very large, and it doesn't really scale that well. And that's the real problem. So these guys cause difficulties, and I've not even considered the goal assignment problem, which goes as n factorial. So in a discrete setting, this becomes exponential. In continuous settings, this is not a problem. This is always a problem because of the number of binary variables in this mixed integer formulation. And then this n factorial is just the goal assignment problem. So these are all the complexities that come in when you try to do coordination, and the number of robots increases from 3 to 5, and beyond 5, it's actually hopeless to try to solve this in most practical settings. So that brings us to new ways of thinking about cooperative control. So when I want to think of lots and lots of vehicles, there is no way this kind of reasoning is going to work. So let's look at how nature does it. Right? So these are pictures of starlings off the coast of Denmark. There's about 500,000 starlings here. They are doing coordinating, they're cooperating, collaborating. I don't know what they're doing, right? But they're forming these incredible patterns. They're not bouncing into each other and killing each other off. They're forming these patterns for whatever reason. But my main interest here is in how they coordinate to form these shapes. Can we get robots to form shapes like this? And if so, how do we get away from the computational challenges that I just told you about, where the methods I told you about are guaranteed not to work beyond the fingers of one hand? Right? Okay, you can say, I'm going to wait for faster computers. Maybe it'll be 6 fingers, not 5, right? But it's going to be hard. So rather than try to mimic what birds do, let's try to understand how you might think about it from a standpoint of nature, right? So I want to throw at you 3 organizing principles, 3 architectural design concepts. The first is, actually I have some more examples that I want to share with you first, so I'll come back to that in a minute. So these are with ants, and this I find incredibly fascinating. Again, these ants are collaborating. They're trying to form. They have to get it, so this area is getting flooded. They have to cross over to the other side. And the only way they can do it is by actually creating this bridge. And they're climbing on top of each other, and they're creating this bridge. Again, here the task is well defined. By the way, this is the same task that I told you before. This is actually it's cut out of plastic. And the reason the ants are carrying it is because we coat it with the juice from fig, and then they think it's food, and they carry it. The nice thing about this is we can tell who's pushing, who's pulling, and who's not doing anything, and just going along for the ride, right? So you could actually try to determine how this cooperative task is being accomplished. So in all of these, I would claim that there are 3 organizing principles. The first is Individuals act independently. There is no queen ant is saying, hey, you need to do this, you need to do this, and so on and so forth. Same with the birds, right? So all robots need to compute their own actions, and they have to do it independently. Second, there's this notion of only local information. So ants at this corner probably are not aware of ants back here, right? This ant may only know about her immediate neighbor, and that's it. Okay? Then the third is this notion of anonymity. That means I don't care who my neighbor is. I don't want to know her name. I don't want to know her color, right? And I don't want them to know who I am. And the paradigm of cooperation should work, right? The minute you say, well, I can only lift this furniture if my best friend is at the other end, you're not going to be able to cooperate and accomplish most tasks, right? So there's got to be this notion of anonymity. So we've tried to do this with robots, and I want to tell you 3 ideas that we have used which leverage these 3 organizing principles. So the first idea is one of leader-follower networks, where in fact robots essentially keep track of just their neighbors. So I is worried about J. In particular, it's worried about the difference of where J is and where I is. So these are the separation variables. Now these separation variables are 4x1 vectors. They consist of positions, x, y, z, and they consist of shape angles. Sorry, the bearing angles, the psi. So these are 4x1 vectors, the exact same 4 variables we use to define the flat coordinates for a quadrotor. And there are many of these vectors, depending on who can see who and who's talking to who. So there are some robots that are aware of the global task, and the global task is specified as a trajectory in the position and your space. So imagine now you have 100 robots, maybe 2 or 3 of them know what overall trajectory that needs to be followed, and the others are only keeping track of their neighbors, right? So you can show if this is a connected graph that in fact the entire team can follow the trajectory. So here's a cartoon video, if you will, work by Katie Powers that illustrates this. So this guy here is a host for a PBS, Public Broadcasting Service station in the US, and episodes called Nova that air every Wednesdays. So this shows how the leader-follower concept works. So these robots are talking to each other, and David has essentially hijacked one of our robots and pulled out the battery, and he's basically commanding it. So that robot can talk but cannot do anything, right? By manipulating that robot, he's essentially able to manipulate, okay, this is not a swarm, but that's because my lab is quite small, but essentially it illustrates the idea. What he's doing with his hands are irrelevant. This is not a human-robot human-robot interaction experiment, but you know, he likes to do theatrics, and that's what you're seeing there. But this is a very, very simple idea. Same idea with this notion of anonymity, and this is really Matt Turpin's work. Just like the experiment I showed you with Luis, they've been asked to form a shape. In this case, it's a circular shape. And by pulling some robots out or putting them in, he alters the dynamics. And once he puts a robot in, neighbors recognize that, and that change propagates throughout the network. If you look from the top, unfortunately I don't have the top views, they're essentially trying to form a circle, the best of their abilities. And the algorithm is invariant to the number of robots and their identities, what IP addresses they have, for instance. So all of that is happening, is actually immaterial to the outcome of this event. So the key idea and the technical idea is that the assignment problem and the planning problem are solved concurrently. And this is the subject of Matt Turpin's thesis. And so remember, this is if you discretize it, this is an exponential with the number of robots. The assignment is n factorial, and the obstacle avoidance and interaction goes as the product of the number of robots and the number of obstacles. So we want to combine all of these problems, and the amazing thing is that this algorithm is only order n cubed, the one I'm going to share with you in a minute. So what's the key idea? So the key idea is very simple. Imagine I asked this robot and this robot to go to this goal and this goal, right? And imagine I did something stupid, and I said, I want this guy to go here and this guy to go here. That's phi 1, right? What's the other option? Phi 2. So it turns out that if you pick the shortest path for both the robots combined, you'll always pick phi 2. You would never pick phi 1. So by ignoring the potential for collisions, and by simply saying, I'm going to find the best trajectory possible, you'll automatically pick phi 2, which avoids collisions. That's the central idea. So forget about collisions. That's where the complexity comes in. Let's completely forget about it, because this theorem says, at least in the plane, and for point robots, this is true. Now, if I take n robots and I form this cost functional, which is basically saying minimize the total distance traveled, I'm always going to prefer this assignment over that assignment. And essentially, I can show that these are free of collisions. That's the central idea. What if there are obstacles like this? And what if I have to consider dynamics? And things get a little more complicated, but I'm going to illustrate this with, again, a very simple example. Imagine robot at SI, robot at SJ, and imagine these are the two goals. Right? How would you assign these? Should I go here or J go here? If J goes here, I might not be able to go through this. Right? Likewise, if I goes here, J might not be able to get there. So it's not immediately clear you can solve this in vacuum. So here's how you might go about solving it. First, you enumerate all possibilities, and you solve for the cost function for all possibilities. In this case, there's two. I going here, J going there, or J going here and I going there. And you solve for it. Shortest distance path, free path, and this you can do in essentially by doing a single robot planning problem. Okay? The second thing you do is you find the cost matrix for every assignment. In this case, there's only 2 assignments, and you found the total cost for each assignment. Okay, then you do the assignment based on which assignment is better in terms of cost. And this turns out, using the Hungarian algorithm, it turns out that this is an order n cubed problem. So this will tell you that this guy needs to go here and this guy needs to go there. Why? Because if you do it the other way, this going there and this going here, the total cost is more. Then the third, you have to essentially establish some level of prioritization or partial ordering. And there's a simple test for it, and this has to do with looking at the shortest distance separating the start location of J and this trajectory, which is this perpendicular distance, and looking at the shortest distance from the end point from this trajectory, which is this little thing, and asking which one is bigger, right? Is this less than 2r? Is this less than 2r? In this case, if that's the case, then J gets priority over A. If this is the case, I gets priority over J. And it turns out in this case, this is true, right? This is actually less than 2r. So I gets priority over J, so this guy will go first. And that's how the priority is assigned. So once you do that, you essentially reparameterize your minimum snap trajectories so that I goes before J. All right, so this incorporates dynamics, it incorporates the best routing, and it solves the assignment problem, and this turns out to be order n cubed. So for instance, this is just a simulation, but it shows you the kinds of things we can do. For some reason, this video is not playing. So you'll see I don't know, this is 100 robots starting from different configurations. They're told to go to goal locations, and on MATLAB, this can be solved in 2 or 3 seconds. In this fairly cluttered environment, and again, these are identical robots, and we're not telling them who needs to go where up front. So they're determining that, and they are finding safe solutions as they go through this. On real robots, the key is, so look, if you look on the top, this is a product of discrete planning. If you look at the bottom, this is where the dynamics have been incorporated, and you have smooth trajectories. So both the plans on the top and the bottom are the same. The bottom one is refined and incorporates dynamics. And in both cases, they're flying through this maze that we constructed to show how robots can go in 3 dimensions. In each case, there's a little circle, which is approximately twice the diameter of the little robot, and it's able to navigate this. And with smoothing, you can run many, many robots. And here's a case where there are 8 robots, and now they're asked to form different shapes. The only obstacles are the other robots, and Matt again specifies the shape, how the shape needs to change as a function of time, and the robots essentially determine how to converge to the shapes and how to avoid each other while doing it. And you see the shapes starting out from a circle, a rectangle, distorting into a circle, then an ellipse, a straight line, back into an ellipse. And all of this is based on equations. So now the paradigm is, if I told 500,000 robots, I don't have 500,000 robots, but if I did, I say, go form the structure that I just saw the Starlings perform. The robots could essentially go off and then approximate this 3-dimensional structure quite efficiently. Again, it's an order n cubed, so it's going to take a while, but it won't be prohibitive. At least you can do it maybe in several minutes. And the largest we have done is really 20 robots. So this is 20 robots, and again, now the shapes are being determined based on what they see in the environment. So 3D to 2D. Again, this shape is mathematically described. Here you see the 3D collapsing to 2D, and now you see how the 2-dimensional shapes essentially change based on features in the environment. But the basic idea, again, is form shapes in a prescribed way so that you could actually achieve the task, and the robots are not specifically told where they need to go to. Let me pause and see if you have any questions before I proceed. There's got to be questions. I've been talking a long time.
I would like to know, everything is done in a centralized manner.
Yes, so this is always the question I get. So yesterday I showed you this block diagram. There's some parts that are being on board the robot, some parts that are being done in the camera network, and some parts that are being done on a workstation. So the central algorithm, which is assigning robots to to goals, is being done centrally. But there's no reason why you couldn't do that in a distributed way, right? So we've done 2 things. One is you take the exact same algorithm, and if everybody has the same information, the outcome will be what you just saw. The other is you give everybody different pieces of information, in which case if you have robot A going here, robot B going here, and they come close to each other, they have to recognize, they have to communicate, and they have to exchange goals. So this is the optimal trajectory. But now what will happen is if they come close to each other, they're going to do that. And that will be suboptimal. So everything that you see here degrades in that sense. But what you saw here, yes, all the solutions were computed centrally, all the assignments. Any other questions?
In the video, we see that the robot is the same. Is it possible to interact with different robots that use flight parameters different? A smart robot with another big?
Right. So the assumption we're making is that the robots are homogeneous. They're identical. So replacing one with the other is not going to lose any functionality from the standpoint of the task, right? That's the question you're asking. And in the case of heterogeneity, you cannot use that. So what I presented here is only true for homogeneous robots. For heterogeneity, we just started looking at this problem, and it turns out to be very difficult to form a general theory. For small numbers in uncluttered environments, you can solve it. But if you have lots and lots of numbers, large number of robots, so let's say you have 1 million robots with 100 different types, and they're all tightly constrained, then it becomes very hard. One way of doing it is by solving them in terms of one type by another type and then another type. So you do a partial ordering across the types. That reduces to this problem. But to do them concurrently turns out to be harder than one might expect. Okay? How much time do I have, Guillermo?
Okay.
15.
Hi. Is there any work being done where you add one or more robots in an adversarial condition, like they want to stop you from achieving the minimization of your goal?
Did you say adversarial?
Yeah, you add one or more robots that try to disrupt the work that's been done.
Yeah, no, we've not done that. I mean, one way of looking at proving that coordination is successful is by assuming that some of the robots are actually adversarial. And you might try to prove that even if you have adversarial robots, they can successfully collaborate or cooperate to perform the task. That's definitely a great line of scientific inquiry. Okay? So let me just conclude with some thoughts about possible applications, at least applications that we're interested in. So one application we're very interested in is actually how we might coordinate ground robots like this, which our colleagues at Tohoku University have been developing, and aerial robots like this, which we've been developing. And this is a 3-year-old picture. And I'll show you this video that kind of illustrates how these robots might collaborate. So here you see our aerial robot sitting on top of the ground robot. Now, it's hitching a ride because we want to save power. So our robots are programmed to be lazy, so whenever possible, they sit on the ground robot and take a ride. But you'll see that when the team actually gets to an obstacle, which the team cannot together cross, like this collapsed doorway, our robot takes off and is able to enter this room and is able to climb over or fly over this bookcase and look on the other side, which the ground robot could never have done in this particular setting. And you can imagine settings where it's unsafe for humans to do this. And you can see our aerial robot developing this 3D map over here. And that 3D map is also being developed by the ground robots. And so together, they go into these different rooms, and they're building a 3-dimensional map, which ends up looking like this. So this is the map of the 9th floor, the 8th floor, and the 7th floor of the electrical engineering building at Tohoku University that with 5-centimeter resolution, we're able to build an entire 3D reconstruction, which tells you something about the structural integrity of this building. So this kind of information would be valuable in first response after earthquakes or other kinds of disasters. Except, what's the problem with this? This experiment, although it was done completely with robots, so humans had nothing to do with it, took 2.5 hours. So after an earthquake, no first responder is going to wait 2.5 hours for you to send your robots in and get the information. They'll give you at most 2.5 minutes, perhaps even 2.5 seconds, right? Because they want to go in. If there are any victims, they have to rescue them. So I think that's our challenge. Can we build a swarm of robots that can do something like this in 2.5 minutes? And the answer is you should be able to if you build these robots that are not expensive, You don't care if half of them actually die in the process, right? And they collect the information, and there's a way to aggregate this information using a cloud of computers that might be located outside the building. You should be able to do this sort of thing just with large numbers. And that's one of our challenge problems. So a related challenge problem is, how do the robots decide where to go to collect information? And yesterday we were talking about how to detect viewpoints for exploration, how to detect frontiers. So one of my students, Ben Charo, has been looking at this idea of using mutual information. So if you look at this objective function, I represents the mutual information of the map and the sensory observations. And the sensory observations are made by robots taking different trajectories. So if I determine what xt the robot takes, that tells me what sensory observation the robot is likely to make and how much that will tell me about the map. So by taking this mutual information and finding trajectories that maximize the mutual information, I get the most optimal information-seeking strategies. So we can do this for heterogeneous teams, for aerial robots and ground robots. The trajectories I'm showing you is only for a ground robot, but by evaluating this type of an integral for both robots, I can determine the best possible strategies. Instead of using something similar to what I showed you yesterday, where these 4 quadrotors are exploring this environment, each of these colored blobs represent frontiers to explore, and robots are assigned to these frontiers using an assignment strategy similar to the one I talked about earlier. And as they do that, they build this map. So either one of these strategies can be used for hundreds of robots, let's say, to explore an unstructured, collapsed building. Just to show you the kinds of strategies we might get, so this is essentially one of our ground robots on the top and one of the aerial robots on the bottom, again, exploring trajectories and concurrently mapping the environment. The information that the ground robot gets and the aerial robot get, these are complementary. So this is truly a collaborative framework where the ground robot can never look on top of a table, and the aerial robot can never look under the table. So, but if they collaborate, they can get this 3-dimensional model, and that's what's being shown here. And you can see that the entropy associated with the map is declining as a function of time, monotonically, or at least the expected entropy. And together they can construct this 3-dimensional map, and this is the area right outside our lab. And so both these robots are doing this. And again, you have to remember they're starting out with no information about the environment. So I want to conclude, but let me do this on a light note. I want to show you this video clip that my former students now at KML Robotics created. I hope this video plays. Yeah. Or I can use my microphone.
Pode, Fábio, aumenta o som, por favor.
So this is fun, and at the end I'm going to ask you a quiz, so you better watch this. So I don't know what quadrotors have to do with Lexus cars. But anytime a company like Lexus gets interested in quadrotors, it's good news for all of us, right? So the question of this is how much was real? That's the question. Any thoughts? Huh? Well, that's what I'm asking you. So on a scale of 0 to 100%, where 0 is nothing was real, everything is computer graphics, 100% everything is real, pick a number. Huh? Okay, well, let's watch it carefully. Now, you know all the math that I talked about, right? So you know what is workable for large numbers, and this is all based on this mixed integer quadratic programming style framework. So if you go back, I'm going to play it without, I'm going to turn off the,
sound?
yeah, I just want to play it, that's all. Ah. So if you look at individual motions, these are all real, right? Every one of these is realistic and it was all shot in a studio. Actually, if you go to the website, you'll see each one of these is shot by a single robot that's actually able to execute these maneuvers. And then at this point, you know that there's some computer graphics editing going on. So these motions are all correct, but it's easy to edit and duplicate these motions. And clearly, when they enter into the elevator, there's no motion capture camera system, and they fly into the sky, you know, all of that is computer graphics. So if your answer was about 25% is real, and the rest is sort of edited, you're probably somewhere in the right ballpark. But you should go look at the Amazing in Motion website, and they tell you how every little bit of this was created, where the technology was, and where the graphics was actually used. But regardless of what you saw here, I want to show you this new movie that's coming, The Swarm. This is a Warner Brothers movie. Actually, some of you are old enough, you might actually have seen this movie. This is actually an old movie. How many of you have seen it? There's a book. It's a horrible book. But the movie is even more horrible. So if you haven't seen it, don't see it, right? So it's about the killer bees that attack and try to kill people. But I like this poster because everything is correct here. Its size is immeasurable. I hope some of the work that I've shown you suggests that. Its power is limitless. This is also true. Its enemy is man. Actually, today we can do lots of things. But we, human beings, are yet to conceptualize ways of actually incorporating this into society so they can actually help us do some of the things we don't want to do. So in some sense, we're standing between robot swarms and their ultimate progress. So that part is also true. But regardless, the swarm is coming. Thank you. I ran out of time. I'm out of time, so.
We have time for
Yes.
I assume that when you go for a large number of robots before testing the experimental platform, you have to simulate it. What kind of simulator platform you have to test that kind of algorithm?
We use multiple simulators. The fact is, so there are two aspects of simulation. One is to simulate the performance of the algorithms. The second is to actually test the software that eventually will find its way into the robot. For the latter, we use something called ROS, which is a robot operating system, and that allows you to simulate large numbers while ensuring that the software abstractions are such that you can go seamlessly from software into hardware. The problem with ROS is that currently it's very hard to do anything more than 5 or 6 robots. So we can't really use ROS. But for all the algorithmic testing, we use MATLAB, and then we have our own simulators on MATLAB. And the process of actually going from software to hardware is something that we have specialized ourselves based on a combination of MATLAB and ROS in our lab, which only works with our robots. So there is no such tool out there right now. Any other questions? Yes?
For robots flying operations, necessarily AI?
You're asking if this is AI or not? You're asking me this question, if it's AI or not? Okay. So I don't know. If you think about one of the problems in AI is you want a swarm to behave collectively to perform things that individuals cannot perform without specifying individuals what to do exactly. Right? So to me, that is AI. So in some sense, what we're doing is striking at one of the core problems of AI. But the methodologies we're using, I mean, AI, the old-fashioned AI, if I may call it that, has a certain way of going about how to specify tasks, how to write instructions, and so on and so forth. That we don't use. The language you use is based on dynamical systems theory, based on mathematics, and then how do you take that and generate software with it, and algorithms, of course. And so in some sense, the knowledge base is slightly different. Yes?
In many of the applications you considered, maybe you have considered that you have to keep connected in terms of information. Have you considered the case where you lose this?
Absolutely. So in order for a group to behave cohesively, the issue of communication is very important. And in the short time, I've just ignored everything about communication. In fact, in a talk I gave last week, and everybody criticized me for it, I said, why care about communication? I mean, look at all of us. We're all hooked up to the cloud. We all have cell phones. So robots someday will all be hooked up, and we don't have to worry about communications. Now, reality is that's not true, but and we have thought about the problem of how to maintain communications, but in this work, I've not presented that. So the problem with robot swarms is you can think of so many different ways to try to break it, and you have to make some assumptions. And the assumption we're making is that someday we'll never have to worry about communication, right? However, for real-time operation, you cannot rely on the network, which means you have to have local onboard autonomy to survive, even though your connection to the cloud is cut. And that we do worry about. Yes? For the little robots, yeah. So we use ARM architecture-based microcontrollers, and then gumsticks processors. The best value we've found are in these Odroid processors, which hard kernel makes. The Odroid XU3 can do everything that we've talked about thus far on board. All the algorithms, including the 3D reconstruction, I think we could do on board. Well, maybe not dense reconstruction, but enough to do obstacle avoidance, I think. This is your time, so yeah.
In nature, probably ants or bees, they do not solve quadratic equations. So how can you relate this to the real behavior in nature of the swarms? Or it's not possible to do that?
So I agree. I think it's dangerous to extrapolate too much from what you see from nature. And I think I said this earlier. We don't see 747 flapping their wings when they fly. So we want to be inspired by nature, but to mimic them would not be the right thing, unless you want to learn about how they work. So I think what ants do, or what bees do, or what birds do, is very different from what we want to do. Birds are not interested in mapping the interiors of rooms. Ants are not interested in carrying furniture to where we want them to go. So I think you have to think about what kinds of problems nature wants to solve, and these are they're evolutionary problems over many, many generations. And then from that, you have to abstract principles that appeal to the kinds of problems we want to solve. So I think it's good to study nature. It's good to study engineering problems and then link these together. But to say I'm going to replicate these methodologies in actual systems, I think would be a little bit of a stretch.
Professor,
Yes.
correct me if I'm wrong, but it seems that speed is a kind of limitation, especially when you are indoor spaces. It's due to the hardware speed or the robustness of the controllers?
I think, so the maximum flown outdoors is about 50 kilometers per hour. So that's like a car, right? I mean, so that's pretty good. Indoors, the main problem is being able to perceive the environment with the resolution you need and the fidelity you need to operate safely. It's not the mechanics, it's not the control, it's not the estimation. It's actually looking at the three-dimensional environment, reconstructing it, and saying this is an obstacle, this is not, and so therefore my trajectory should go this way, and that's hard. Yeah.
Professor, I have shown in lab that you have only had about 20 robots that were simulating this war. But when it comes to real robots, when we scale this up, what are the biggest problems that we might have when we have actually like thousands of robots flying and doing a specific task?
I think our biggest problem is robots operating close to each other and thinking about recognizing each other and avoiding collisions. Actually, I suspect that nature doesn't do it. If you look at birds, they fly really close to each other, and they actually touch each other, and because of that, they can feel their way out of problems. If I told all of us to evacuate this room in 5 seconds, I bet we could do it. But we'd bump into each other, and you know, we'd all come out unharmed, right? And robots are not good enough for that yet. I think our big... Sorry?
We know people
who drive like that, exactly, yes. Yeah, right, yeah. Yeah, and I come from India, so I can admire the way Brazilians drive. So, right, that's true. So I think there's if we knew how to make soft robots, if we knew how to feel each other, then I think the demands on perception are considerably lower. I think to me that's a huge challenge. Yeah.
Okay, guys, I think this is very nice, but I have to finish. So let's thank Professor Kumar for the last time.
Thank you.
Thank you very much. O pessoal pediu para avisar que a próxima apresentação vai começar em seguida. O café vai ser no intervalo da segunda apresentação, ok? Então, quem quiser dar uma andadinha aí para esticar as pernas, mas voltem agora, só o professor instalar para a gente voltar.